ladies and gentlemen, boys and girls. My name is Mr. Do, and science is my business. Welcome to Mr. Do Science World, and today we're going to talk about work-energy theorem. On the last video, we spoke about power, we've spoken about energy, and we've spoken about work. Today we want to combine work and energy together, and that is what we refer to as work-energy theorem. Before I give you the theorem itself, let's try and look at the way to come out with a theorem mathematically. Alright. We started by saying that work. So if you remember, I said that when we talk about work, we can look at work from the point where there are different forces that are acting on an object. So because different forces are acting on the object, we can talk about what? The net work done. So I can say that W net, which is the net work done on an object, is equals to the net force acting on an object, which means the sum of all the forces acting on an object multiplied by the what? The displacement. Okay. Now, if I look at it from this point, we can use delta x, we can use d. It doesn't matter which one you are using. So let's look at it from the points here. This is the formula itself. But what do we know about F net? Okay, according to Newton's second law, F net can simply be what? It can simply be written as what? MA. That is the mass times the what? Acceleration. So I can simply say that my W net is equals to MAD. I can hear somebody said mad. Well, that's okay. No problem. We are trying to come out with something. We are not mad yet. We'll come out with something important. Now that we have seen this, let's try and find what an acceleration is. By definition, we said acceleration is the rate of change of velocity with respect to time, or the rate of change of velocity. So, alright, so the rate of change of velocity simply means we can look at it from the equations of motion, which says Vf squared is equals to Vi squared plus 2 what? AD. Okay, what is the Vf squared? This is Vf squared. So what is Vf? Vf is the final velocity, Vi is the initial velocity, A is the acceleration, and D is the what? Is the displacement. Right. Let's see. I'm going to make A the subject of relation. And if I decide to make A the subject of relation, I can look at it from this point and say I'm transposing this to this side. So therefore, after transposing this, I'll divide it by what? The 2D. So it will look like I'll say A is now equals to Vf squared minus Vi squared divided by what? 2D. Okay. And that is from the what? Equations of motion. Now I have med here because I am not med. I want to change the med and make it look something different. So let's look at it from that point and say that, okay, W net is now equals to what? M into, in place of A, I am putting this there. So that is Vf squared minus Vi squared all over 2D. And remember, there is another D. So I put it there. What have I gotten now? Well, there is a D here, there is a D there. I can cancel out the D because one is a denominator and one is a numerator. So mathematically, it is possible to cancel out one. So I can simply say that F net, W net is now equals to M into Vf squared minus Vi squared. Okay, and what do I have? Divided by 2, because now I'm left with just 2. Something interesting is coming out. So let's look at it. If we look at this as a physicist, what can we see? What we can see is that we can try to find out and write this in terms of this again. This can be written, I'm taking out this 1/2 out, and then I'll be left with what? Okay, let me take 1/2 m out, so that I will be left with what? Vf squared minus Vi squared. Good. Now, this is half m into Vf squared minus Vi squared. Immediately this is out, what should come into my mind is that we learned something earlier about what? Energy. And that energy that we learned about, this can be what? We can expand this and write it so that we can look at the type of energy that we are speaking of right now. So if I want to look at that, let's look at it and see from that point in time and see what we need to do. Okay, I am going to clean the side. Okay, sorry. Now I can write this as W net is now equals to half m into, or half m Vf squared minus what? Minus half m Vi squared. What do we know about half m Vf squared? We know that anytime that we speak of half mv squared, we are speaking about a particular type of energy. What type of energy are we speaking of? We are speaking about what? The kinetic word energy. So these can represent a kinetic energy, and these can represent a kinetic energy. What type of kinetic energy? Here, because we are speaking of Vf, so I can say the final kinetic energy minus the word initial kinetic energy. So these can be written as W net is now equals to Ek final minus what? Minus Ek initial. And what is Ek final minus Ek initial? That brings us to look at something in physics. Whenever we are looking at a change in something, when we look at the difference between two things, we say a change in that. So this simply means a change in what? In kinetic energy. Therefore, I can say that W net is equals to change in what? Change in kinetic energy. Change in Ek. And this is what we refer to in physics as well as work energy theorem. So what is work energy theorem? This is the mathematical definition of work energy theorem. So we can say that work energy theorem simply states or stipulates that the net work done on an object is equal to the change in kinetic energy of an object. And that is what we refer to as work energy theorem. Now, general energy theorem. We can speak also in terms of the work energy theorem as a non-consecutive forces. So we can say that WNC is now equals to change in kinetic energy plus change in potential energy, where WNC is equal to the work done by a non-consecutive force. Now, when we say a non-consecutive force, what do we mean by a non-consecutive force? A non-consecutive force includes friction, air resistance, tension in cord, push or pulled by a person, a rocket, or a motor propulsions. These are all a non-consecutive forces. The work done by these forces depends on the path taken from one to another. Now, that means that whenever we speak of a non-consecutive forces, we are talking about a force in which the work done depends on the path taken. So now let's look at the different types of consecutive forces and a non-consecutive force. Right. For non-consecutive forces, the R friction, L resistance, tension in a cord, motor or rocket propulsion, and then we can talk about a push or a pull by what? By a person. When we talk about consecutive forces, they include gravitational force, elastic force, or electric force. Now let's look at some scenario. Considering a car whose brakes are being applied, the braking force is in the opposite direction to the car displacement, which simply implies that the force and the displacement are in opposite direction, and that means that theta is now equals to 180 degrees. And when we look at that, because we are pressing the brake, there is a decrease in velocity of the car from V1 to to V2, which means the initial velocity is now going to be different from the final velocity. So the work done by the braking force will be given by the formula W is equal to Fx cos theta. And once we are looking at it from that perspective, it simply means that our W will now be equals to F times cos 180 degrees. Fx cos 180. That means 180, when you look at cos 180, it's equals to negative 1. So finally, our W is now going to be negative Fx, which means work done by that frictional force is going to be is going to be a negative work done. Now let's try and look at some problems. So let's look at question number 1. It's time for questions. Question number 1. A force of 6 newtons is applied on a box of mass 2 kg as shown in the diagram if the angle of inclination is 30 degrees and the distance the box can travel is 20 meters. Determine, without using kinematic equations, the velocity of the box when it reaches the bottom of the incline. The box experiences a frictional force of 2 newtons as it slides down the incline and is initially held at rest. Okay, now let's solve the problem. And when you look at the problem that we're given, this is just the pictorial view of the problem. This is the inclined plane, and the inclined plane is at 30 degrees. We were told that the object which is found on the inclined plane is 2 kg. The applied force is 6 newtons. The frictional force is 2 newtons. And the displacement from the bottom of the incline to the top of the incline is 20 meters. Now we want to find the velocity with which this object will use in reaching the bottom of the incline. Now, what do we need to do? We need to look at the applied force. So we are considering the work done by the applied force. We will say that the work done by the applied force is equals to the change in the kinetic energy plus the change in potential energy plus the the work done by the Okay, so here is the change in kinetic energy or work done by kinetic energy, change in potential energy plus the work done also against against friction. Against the friction. So work done against friction is here. The change in kinetic energy is here. The change in potential energy is there. The sum of these 3 things here must be equal to the work done by the applied force. Now let's see. What is the work done by the applied force? The work done by the applied force, it's simply the applied force itself multiplied by the change in displacement multiplied by the cos of the angle between the applied force and the displacement of the object. Let's look at it. The applied force is up the incline, but the object is being displaced down the incline. Therefore, the applied force and the displacement, they are just opposite to each other, creating an angle of 180 degrees. So in this case, our theta is 180 degrees. Let's look now and move on to look at the change in kinetic energy. The change in kinetic energy is just simply the final kinetic energy minus the what? The initial kinetic energy. So where is the final kinetic energy? The final kinetic energy is going to be at the bottom here, while the initial kinetic energy is the point where the object is before it what? It started its motion. Because at that point the object was not moving, the kinetic energy at that point is going to be what? It's going to be 0. So I am going to have half mvf, which is the final kinetic energy, minus the initial kinetic energy, and there is now a change in potential energy. So change in potential energy is also the final minus the initial. Let's look at it and see. I am here, there is a certain height, and now I move down here, there is no height. So the initial, there is a height, but the final, there is no height. So the final potential energy is now going to be what? 0. But the initial potential is not 0. So I'm going to have mgh final minus mgh initial. And the next thing that is left is the what? Is the work done against the friction. The work done against friction is just simply what? Is simply going to be the force of friction multiplied by the change in x, which is the what? The displacement, the change in displacement. Okay, we're going to do the substitution now into this equation and solve for the problem. So let's look at it and see. What is the applied force? It is 6 multiplied by the displacement, which is 20, multiplied by cos 180 degrees, and that must be equal to half. Here we are looking for the final, so that is not 0. So multiply by 2 multiplied by v squared, vf squared. This is 0, so minus 0, plus the initial for this particular one, it was at a certain height. Okay, the final one is here, so the final is going to be what? 0. So 0 for the height multiplied by g multiplied by the mass must be 0 as well. And now minus what? 2 multiplied by g, which is 9.8, multiplied by the height, and the height is now here. Check for the height. The height is here. This is the opposite to the angle, and this is the hypotenuse. So for us to look for that, that is going to be what? The hypotenuse multiplied by what? The sine of that angle, and that is going to be what? 20 sine what? 30 degrees. And what am I going to do? I raise plus. What is the friction? The friction is now 2 multiplied by delta x, which is the displacement, and that is 20. So 20 is on the side. Check it and see. If I multiply this, cos 180 is going to give me what? Negative 1. So negative 1 multiplied by 20 will be negative 20 multiplied by 6, that is negative 120. So I'm going to have negative 120 is equal to, this 2 is going to cancel this 2, so I'm going to left with final velocity squared. And now I'm going to multiply negative 2 multiplied by 9.8 multiplied by 20 multiplied by this. And what are we going to have? We are going to have negative 196. And then I'm going to multiply 2 by 20. and that's going to be what? 40. So I have 40 there, and now what I want to look for is the what is this. So what do? I'm going to do transposition. This remains here, this goes there, that goes there. This and this is going to be negative 160 plus this. So this is going to be 196 minus what? 140. So sorry, 160, because this and this is 160, and that must be equals to what? Vf squared. So what is going to be my Vf? My Vf is now going to be this and this. Okay, let's start from there. Vf squared is now going to be this and this is going to be what? 36. And now I find what? The root of both sides of the equation. And once I find root of both sides, my Vf is now equals to what? It's going to be 6. So 6 what? This is velocity. So that is 6 meters per second. Remember I said to you before in the other video and said this also can be written as 6 meters per second. This and this is the same. So the velocity with which the object is going to use to go down the inclined plane here, at the bottom here of the inclined plane, we are going to have our velocity to be what? 6 meters per second. Now let's solve question number 4. A truck traveling at 55 kilometers per hour can be stopped in a minimum distance of 35 meters by applying the brakes. If the same automobile is traveling at 110 kilometers per hour, twice the speed, what is the minimum stopping distance? Okay, so once we are given this kind of a problem, what we need to do is that we have to know that we are given what to find. We are given two different what velocities, and we are to find the distance. So to find the distance, what we need to know is that we are trying to compare distances, because there is a certain distance which is at the initial stage and there is a final distance that we are looking for now. So since it is work done by friction, when we look at a problem, it is a work done by friction between the tires and the road that causes the what? The kinetic energy of the moving vehicle to the zero or to zero. We can use the following equation to solve for what? For the distance. So what do? We can say that, remember we are talking about a friction, and friction is a non-consecutive force. So we can say work done by the non-consecutive force is equal to the change in kinetic energy plus the change in potential energy. In this case, there is no change in potential energy, and the non-consecutive force causing the work kinetic energy to change is friction. So therefore we can write the equation as work friction is equal to change in what? In kinetic energy. Because we have said that the potential energy is equal to what? Is equal to zero, because there is no change. Right? If work friction is equal to change in kinetic energy, then we can simply write that as W friction is equal to EK final minus EK initial. What is the work friction? The work friction, as we have said, the work is always what? Done by friction, and that kind of a work done is a negative work done. Therefore we can say negative FF multiplied by the distance, because we are having the distance become what? The angle created between the direction of motion and the friction to be what? 180. So we can write it as negative FFD is equals to 0 minus half mv squared. Well, the final velocity there is 0. Therefore, the final kinetic energy is also what? 0. So we can say from this point and make D the subject from this point to say, okay, our D is therefore equals to mv squared all over 2ff. And once we have that, we can then solve for this particular problem to say, since the distance is directly proportional to the v squared, we can write a relationship between the two distances using the known velocities. So we can say d1 over d2 is equal to v1 squared over v2 squared. And then we can do the substitution from this point. What is the value of the d1? It is 35 according to the question. d2 is what we're looking for, so we can say 35 over d2 is equal to, what is v1? v1 is 55 according to the question, and v2 is 110, so we can say 52 squared all over 110 squared. And once we cross multiply, we're going to have 35 multiplied by 110 squared divided by 55 squared. And that is going to give us d2 is equal to 140 meters. That is the distance that is going to be what? That we are going to cover as a result of what? The change in the what? In the velocities. Remember one thing, that all the time that you are given a non-consecutive force, you have to look at it to see whether you are given whether the potential, the change in potential energy is 0 or not equal to 0, and then you can do your substitution. Thank you very much for watching this video, and I hope that you have learned a lot of things from this point or in this video, and I expect that you go on and look at our revision on work energy and power. See you next time, but please don't forget to subscribe to our YouTube channel, and as you subscribe, click on the bell so that whenever we release any new video, you'll be the first person to watch it. As you subscribe, comment, like it, and share. See you next time. Bye bye.